Have fun.
Okay. Yeah. Welcome to everybody. So I made it just in time to this point. So I had some, I took some wrong routes in Berlin. So I want to give you an introduction to multicast security. It's a subject I got into a few years ago when I was working in the context of a data distribution system with requirements for scalability and fault tolerance, and we came to the conclusion that TLS SSL is not the right choice to implement transport security covering multicast or some kind of scalable event and notification system. So I went into the subject, multicast security, and so I want to give you a short overview now, what it is all about, the different options that exist, tell a little bit about TLS, why TLS is not the right choice in this context. So we'll start with a small use case, multicast fundamentals, comparing security solutions, introduction to secure real-time transport protocol, which is a standard protocol. But I didn't know, well, everybody in the context of voice over IP probably knows this protocol. It was new to me. And I will talk a little bit about group key exchange and the RFC, which are related to it. So as I told you, so I got into multicast security dealing with data distribution services. It's a DDS, or in short DDS. It's a standard which has been defined by the OMG in few years ago, 5 years ago. It's a publish-subscribe platform or middleware, and so it if you know the OMG, probably you associate it with CORBA and client-server architecture. So the data distribution service is a completely different architecture. It's a publish-subscribe system, message-based, net-centric, data-centric. And so far that didn't exist, or that there hadn't existed any secure transport protocol for this data distribution service architecture. So that's what I did. But of course, multicast communication can be used for various use cases. Multimedia conferencing, replicated databases, distributed simulation, active batches that broadcast the location in the network, control measurement systems, and regular event systems. What is multicast security all about? Multicast security is a one-to-many communication. You send one message out as a multicast message regarding a specific IP address and a port, and all these receivers are listening to this multicast address and this specific port, and they will receive the message at the same time. It's in contrast, if you use client-server architecture using point-to-point communication, you would end up with the source sending a message to this receiver, afterwards sending to this one, to this one, to this one, and this wouldn't scale. So you would have a delay. The last one would receive the message n times the delay it takes to put a message to the network. So that's why scalable event messaging systems or notification systems end up with the multicast concept, and the burden to distribute all the knowledge is handed over to the IP-based, to the underlying network. In this case, IP-based, using IP multicast functionalities. So the DDS, data distribution service I worked for, or I looked into the subject, has been specified in 2004. It's a data-centric publish-subscribe system dealing with more than 1,000 nodes in the context of avionics, vessels, stock exchange systems, all different kinds. Automotive, it's getting to be popular. Finance and public transport. The multicast is based on using UDP, using the multicast functionalities, dealing with IP version 4. The multicast address is in a range of 224 to 239, and for example, this is a valid multicast address. So what you need is on the network layer, the group management protocol being activated in your network, and dealing with IP version 6, multicast addresses, IP multicast addresses have a suffix FF00. For example, FF15 is a valid multicast address. In this case, dealing with IP version 6, you've got to deal with multicast listener discovery protocol being activated in your underlying IP network. Otherwise, if you don't have these protocols or management protocols activated, your multicast addresses will not be routed to the specific recipients listening on specific multicast messages. For example, if you activate the listener, you can listen to any network interface and bind or join a specific multicast group, and using this specific setsock operation, and the senders binding to any address or any port, and specifying a specific multicast functionality, and sending a message to this specific multicast address and this specific port. That's how multicast is configured in your client or in the sender and your receivers. The problem you're faced normally in this context is, and in terms of security, is that any node can join a multicast address. There is no restriction on IP layer or whatever that you can restrict a multicast to a specific node in your network. So that, in this case, you come up with the question, how can I protect my multicast traffic not being received by specific nodes? Another issue is any node can send multicast addresses. And in this case, dealing with one-to-many communication, you've got the problem that even if you've got encryption of the traffic, the sender knows the shared secret, but also the recipients must know the shared secret. So you don't have a one-to-one association in a security session as you've got, as you know, from TLS. In TLS, you know, if I receive something and it has been encrypted with a specific secret, I know it must have been sent by the sender. But dealing with a one-to-many communication, all nodes in my network know the secret. And if I receive something, I can't make sure who was the origin of this message. It could have been any other in the network or in this security session. So that's another problem. Another problem is dealing with security on a multicast in a multicast environment is that nodes may join or leave a specific session. So you must make sure that if I negotiated a secret to encrypt my traffic and a node is leaving the session, you must make sure that a new secret is established so that the node which left the session or the group is not able to continue to read the data passively. So what we need is authentication, confidentiality, integrity, non-repudiation. Non-repudiation in terms of who is the origin of the multicast message I received. So there are different features or technologies around which we analyzed if they cover the functionality we need, and I'm wondering if this is the right. Okay, don't look at this. Oh, it is. Okay, it was the right presentation. Okay. So what we had to look at is different technologies to figure out if these are the right choice for our needs. So we had to look at TLS, as this is very popular, and there are a lot of implementations around. And we had to look at if it fulfills our requirements. We had to look at IP security. And in the end, we had to look at secure real-time protocol, which was, in the end, our choice. At least we took some concepts from SRTP and implemented it natively for our application layer, or into our application layer protocol. So why does SSL TLS does not match for multicast communication? At first, it's a one-to-one client-server oriented technology. And dealing with multicast or multicast-based patterns, this using TLS would end up to implement or degrade my multicast and scalable system to a client-server-oriented system. So it would be degradation. In the end, my sender of the data would be required to establish a one-to-one SSL connection to every recipient. So that's something we don't want. Our scalable system would be degraded to a non-scaling client-server architecture. Another issue is SSL TLS is using in-band key exchange, blocking key exchange, which means that when I establish a connection, and as a TLS connection between a client and a server, no data can be transmitted until a secret has been negotiated between client and server. This negotiation is blocking, and at worst, there can happen a renegotiation. Anytime during the connection, a renegotiation can take place, interrupting my data stream and dealing with real-time communication. That would be a mess. The data would be blocked, and it's unclear, or there are no timeouts that might tell me how long the negotiation might take. So this is another issue which makes SSL not the appropriate choice for real-time communication. Another issue is that SSL TLS is stream-oriented and dealing with real-time communication. This introduces a bad feature, namely that in case of network congestions, data might be resent by the underlying stream or controller. And dealing with real-time communication, which must be, we are interested that the data is delivered as fast as possible, or at least within a specific time frame, or never. So best effort. And dealing with TCP or TLS, we've got the bad, we have, Eigenschaft? Eigenschaft of English? Property, okay. The bad property that, that the data might be resent, even if the data has been, the lifetime of the data has expired. So there is to deal with, at least with the best effort problem and return problem, datagram TLS has been specified as RFC 4347, which is robust against packet loss, except during the handshake phase. That means when the handshake and the key or negotiation between client and server is established using UDP, the successing communication using UDP packets can deal with packet loss. But again, as SSL and TLS, and renegotiation can happen anytime during the communication and block your real-time data streams. This is something which you're not, you don't want. So, and still, even dealing with datagram TLS, DTLS, we still have a one-to-one communication between sender and receiver of data. So what we have to look on, let's have, okay. So this is the schema of the TLS handshake. And so it starts with the client hello and with the server, server hello, server done, client exchange. You probably know. You can look at this during in a Wireshark with Wireshark, and well, it just gives you an impression how a handshake looks like. And the problem is that the whole protocol assumes that there is a client and a server. There's always a one-to-one association in between. You can deal with sessions and session keys, session IDs, and reestablish a session, the client sending a session ID, and if the server stored the data, it's reestablished. But again, even dealing with sessions and session reestablishment, you've got a one-to-one relationship. So what we are looking for is a one-to-N communication pattern, UDP multicast. We want scalability, non-blocking key exchange, either out of band or using a separate signaling channel. It must be robust against packet loss. We are interested in authentication, confidentiality, integrity, and non-repudiation. That should be added here. And optional, robust against replay attacks. So having a look at IPsec, you end up with you realize that IPsec has been specified with a one-to-one relationship in mind. Although there are some concepts like you can use tunneling to establish tunnels and encapsulating your multicast packets into IP packets and tunneling these two through to every recipient. But again, you have to deal with separate tunnels, and maybe every tunnel is using a separate encryption, and again, you have got to deal with one-to-many connections, and again, this doesn't scale very well. As in the end, we are dealing with a one-to-one communication at least, and we have got for real multicast communication in a broader network, we have to establish a full mesh between all nodes related in the communication. So in the end, we came up, we had a look at secure RTP as an alternative. So SRTP is secure transport functionality for the real-time transport protocol and the real-time control protocol. It supports unicast, multicast, it's packet-oriented, It protects traffic not only on a host-to-host relationship, but also on an application user or port-specific layer, so it's very fine-grained. It's session-oriented. One aspect is you have got to deal with it assumes, the SRTP protocol assumes out-of-band key exchange and key negotiation. It moves this burden to the application or the use case specific to a use case specific solution. We'll talk about this a little bit later. It's about multimedia internet key exchange protocol, which is related to this. But in fact, the key exchange is not related to the security transport protocol. The key exchange is extracted and must be handled somewhere else. Secure real-time protocols providing authenticity, confidentiality, and integrity. And optionally, it supports replay attacks. And what I think is very important, it can be configured on the application layer, whereas IP security, at least my knowledge, is something you configure on the administration layer, or the administrators configure IPsec in the network. So in this case, with SRTP, you've got a solution which can be integrated into your application, no matter.
Please be quiet. Thank you very much.
No matter what underlying network you're dealing with. If there are any questions, feel free to interrupt me and ask. That's fine. Any questions so far? Anybody? Does anybody have experience with multicast security and SRTP and? Okay, thank you. So RTP has been designed primarily for multimedia communication and stream-oriented communication. In this case, we're talking about a sender and a receiver of data. A sender emitting a data stream, a multimedia stream, to a broad number of, a huge amount of recipients, something like e-learning system, which could be used, or a conferencing system. One source emitting the data and others receiving the data. It can be used also for database systems or storaging, interactive distributed simulation, and control measurement. That's something I mentioned before. So RTP has been defined by RFC 3550 in 2003, so many years ago. And it can be used, it's generic. It's suitable for audio, video, and simulation data. It can deal with multicast traffic, unicast network. And it's over unreliable transport. That means packet loss and reordering. So that's something I didn't mention before. So the security concept has to deal with reordering as well. The RTP protocol is augmented by a control protocol, which is used to deliver acknowledge messages from the receivers to the sender, so the sender can adapt the encodings and maybe use more efficient encodings to save bandwidth. The acknowledging deals also with the case that having a huge amount of recipients that that the RTP or the sender, the real-time control protocol covers also the case that that there is no burst of control messages in your network. So there is a There's also a notion of how often should messages be acknowledged, and the standard RTP standard defines a calculation so every recipient is able to tell how often he should acknowledge messages. So the RTP communication looks like this. You've got a source or participant emitting multicast messages and a number of recipients. And the receivers will reply to the source using the real-time control protocol to acknowledge messages or media streams being received. Having a look at the RTP message header, there is it's a simple protocol with a version number in front, first octet, a sequence number, a timestamp. This is related to the fact that that RTP has been intended for multimedia streams. So by default, it is, well, the real-time transfer protocol contains a timestamp and a synchronization source. This synchronization source tells the recipient which multimedia stream the message is related to. So a single sender can emit multiple streams, every stream with a different synchronization source identifier, and the receivers can tell which stream the data or the packet belongs to. The payload is very simple. You just attach it to the header, and you add some RTP padding at the end. The padding can be important in case dealing with block-oriented encryptions. So when we talk about secure real-time protocol, this has been specified by the RFC 3711 in 2004. It assumes symmetric ciphers to encrypt the traffic. It's using stream ciphers. This has the benefit that the calculation of the stream ciphers can be parallelized. It can be pre-calculated. By default, it's using the AES counter mode, or it could use AES counter with CBC MAC, in short CCM. So the secure real-time protocol is robust against packet loss, and it doesn't, and you don't have the problem dealing with in-band exchange of security attributes during or over the same communication channel as your payload. That means if you have to face a renegotiation, a rekeying, this can be done using a separate channel, or you can achieve this using your application layer protocol. The secure real-time protocol message looks like this. You've got the header, again, some RTP extensions, which are still optional, and at the end, a secure real-time protocol master key identifier, and an authentication tag, which is recommended so that you can tell the origin of a specific data. As you can see, the encrypted portion is just the payload, and the counter mode is using the sequence number, timestamp, and synchronization source as to incorporate into a counter. And based on this counter, the AES counter mode is calculating a stream cipher, and the stream cipher is used to encrypt the payload. In this case, using the counter mode, in fact, RTP padding is not required, as stream ciphers do not require padding of the payload being encrypted. at least not the AES counter mode. Are there any questions regarding?
I found the point very interesting about how the transmission is safe, like the packets actually arrive. You just mentioned it in one point, I'm sorry. The reliability of the packets in secure RTP, how is it realized?
The reliability? No.
Just go back one slide. It's robust against packet loss. How does that work?
So if you use chained block ciphers, you might have the problem that the next packet or the next encrypted block depends on hash value calculated over the previous encrypted block. So if you lose one of those packets, you are not able to continue or to decrypt, or the recipient is not able to decrypt the stream. In this case, with the counter mode, you don't. There is no dealing with the counter mode. You start your encryption using a counter. And what AES is doing is you take a 16-octet block, which represents value of your counter, well, which is the current counter value, and AES encrypts this piece. And now you end up with a more or less random sequence of 1 and zeros. And this one of zeros is used to XOR your payload. To XOR the payload. And so this way you can encrypt 16 octets of your payload. Now you increment your counter to the next plus 1. You have got a new counter, and again, you use AES in electronic, what is it, table? What was the name? Codebook, electronic codebook. So very simple AES mode. And again, you use AES to encrypt this counter. Again, you end up with a new sequence, more random number, which you XOR with the next block of your payload. So what you do is you count up blocks or your number, and you use this counter to create a random stream of 1 and zeros, which is used to XOR your payload, to encrypt your payload. And the receiver is doing the same. The receiver just needs the counters and must count the same way as the sender. So what we do here is we create, or every message I receive contains the counter, the sequence number, timestamp, and an identifier of the stream. And I can use these values to reestablish the counter the sender has used. So I reestablish the counter at least, and I get the starting counter on my payload, and then I just count up until I reach the end of my payload.
All right. So the packets are numbered, and that's how we reconstruct the stream.
Yes.
And if there's a packet loss, then we just get an error. Is that it, or is there a recovery for lost packets?
No, a recovery of lost packets would be handled on your application layer. So it's not dealt it's not handled on your transport layer. It's not handled by a security protocol or transport. It must be handled on the application layer.
is it actually necessary in practice, or do you usually not have packet loss and so it just works?
It depends. Talking about the data distribution service, so it's more like a notification system, notification service. You have got to deal with best effort data and reliable data. And in the context of DDS, these are quality of service parameters. And for every kind of data or notification type, you can configure this. And dealing with best effort data types, it's not necessary to deal with lost packets. And
I wanted to know, in a pragmatic, realistic situation, everyday situation, is it likely to lose packets, or can you just go very far with best effort?
Depends on your network and on the load on your network. If there is no congestion and no packets are thrown away, or few, well, it's a loss will happen rarely, but dealing with burst on your network, it might happen that reliable data is not, well, is facing a packet loss. Maybe you're dealing with fragmented data, and you want to make sure that you're requesting the lost fragment. In this case, your application layer protocol must deal or must keep track which packets are lost, which have not been delivered within time, and so on. So at least this is how it is handled in the DDS environment or framework. In fact, a huge number of systems work very fine with best effort communication. Just imagine having, well, maybe a temperature sensor and in your production environment, and you're not interested in the value 2 seconds ago. You always want the temperature which has been measured 5 milliseconds ago. So in this case, you wouldn't bother about lost packets. But if you deal with logging messages or auditing messages, you might be interested in reliable transport. In this case, you have to deal with packet loss. So what SRTP provides also is a windowing of data. In this, well, maybe it's too fast. So the payload is encrypted using a counter, and the counter is reestablished for every packet being received using the sequence number, timestamp, synchronization source, and then the protocol is able to count up within, or to count the blocks until the end of the payload is reached. So we are always encrypting 16 octets, and then a new counter is calculated, encrypted using AES, and XORed with the payload with the next 16 octets. Authentication is a matter of the payload and the header. So the attached authentication tag is calculated using the blue section and the yellow section. So we can make sure that no one tampers sequence number, timestamps, or synchronization sources. In this case, the authentication can be done using a symmetric key, which has been negotiated between the participants, or it could be done using asymmetric ciphers, RSA, and so on. But in this case, the performance would suffer a lot. So dealing with 2048 RSI signing, you might end up with 1,000 messages or less per second. maybe 600, depending on your hardware. So it would be compared to 40,000 or 60,000 message before, maybe. So it's a real degradation using RSA to calculate an authentication tag. If you know a better asymmetric signing function, I would be very much interested. But these are the numbers, so I've got in mind.
I guess many of us would probably just think about a hash algorithm just doing a hash, but does it mean that hash is actually much more time consuming than symmetric key? Like MD5 and SHA-1, SHA-5, 12, something.
Well, you've got to calculate a hash anyway, and then sign, and then encrypt. So you could use HMAC using a symmetric secret, or you calculate a hash and attach the hash to the well, and the authentication tag would contain the signed or a digest of the signed hash. So HMAC would be cheaper. Yeah. 10 minutes left. Yeah. Okay. So there are different solutions to sign your messages and to make sure that the message to ensure the origin of the message. One problem I've got to point you is the sequence number. The sequence number, so the timestamp should be real time, so it should be your clock on your machine. And in fact, I don't know what's the resolution right now, but for every timestamp, the sequence number will be increased. So just imagine that you send thousands of messages per second. It might happen that your sequence number you might get an overrun and start from 0 again. So the sequence number is way too short, and based on the fact that secure RTP is using the sequence number to calculate the counter, this is the real problem. So if you get out of sync of your data stream, of your multimedia stream, you might not be able to resync again with your multimedia stream, because you cannot tell if the sequence number had an overrun and a rollover, and how many rollovers happened during the time. So to deal with this, the RTP extension has an optional flag or optional parameter to communicate the rollovers of the sequence number which happened in the past. And this is a rollover counter, ROC. So what I recommend is that you use a rollover counter together with SRTP protocol. Otherwise, you might get out of sync in your communication and might not be able to resync your encrypted stream later. So SRTP provides windowing, but the windowing requires that the receivers acknowledge messages. So the sender knows which messages have been received, and a window can be adapted. It realizes confidentiality using AES, authentication, integrity using HMAC SHA-1. So the SRTP protocol provides a context, or a cryptographic context between sender and receiver. It has the notion of master keys, which is delivered in this attribute. And the master key is used to derive a number of session keys, the encryption keys and the authentication keys. the authentication keys which are used to create the authentication tag. So what I already said, shortcomings is rollover counter. You must make sure that the rollover counter is, or your SRTP implementation you're using is able or implements this feature to handle a rollover counter. At least 1 year ago, when I had a look at libsrtp, libsrtp did not implement this functionality or feature. And another shortcoming is that there is little documentation about key exchange or appropriate key exchanges for a group or multicast communication. So there are different possible solutions you could use. ZRTP, which is in-band and using an anonymous Diffie-Hellman authentication to exchange secrets. And one important is multimedia internet key exchange, which implements various modes. For example, RSA or reverse RSA mode, which works more a bit like this. The receiver sends over a public key, and the source replies with a secret which is being used, or with a master key. And the master key will be encrypted using the public key. And the receiver will be able to participate in the session and the communication, multicast communication. That's very simple. And you don't need any centralized key server. That's one benefit. Of course, you could also use some kind of centralized key server, and all the participants access this key server to request the appropriate secrets for a multicast communication session. The group key exchange on multimedia internet keying protocol also provides many-to-many, or a solution for many-to-many key exchange, and a peer-to-peer one-to-many key exchange. So are there any further questions regarding multicast communication and multicast security? So if there are any, you can contact me using this email address, phone, and what I recommend is using this website, which collects or lists all the relevant RFCs in this context for multicast security.
One question. This might be a question for a whole other topic. I'm not sure, but would RTP be the best way to do this sort of thing if IPv6 were implemented?
To do what?
With IPv6.
RTP, IP6 or RTP?
With IP version 6.
IP version 6. It doesn't matter using IP version 6 or whatever. So in fact, multicast communication differs in IP version 6. So it's better integrated, it's better dealt with, but in fact the RTP doesn't bother about IP version.
Hi, just a general multicast question. I was wondering how widely is multicast actually deployed in the sort of consumer ADSL market and things? If you were launching a multicast service today, do you have a good chance that it would be widely supported, or is it still very limited support amongst ISPs?
Multicast?
Yeah.
There's one challenges. Okay, that's what I skipped. Works within LAN very well, but wide area networks across routers is still a problem. So, and you must own, if you want to establish multicast communication over wide area network, you must be administrator of the network and to allow this kind of communication. What you can do is you can establish an IP tunnel of VPN between two locations. and tunnel multicast traffic through this tunnel. So you could connect 2 locations using this VPN IP tunnel.
And is this situation going to improve, and will multicast be generally available with IPv6?
I don't know. I don't think that I don't expect that multicast communication will be available over, will be supported by ISPs in future. So I don't expect this.
I have a question about the rollover counter.
Yes.
When it's present, is it included in the calculation of the key stream?
It's the rollover counter. What was it? The rollover counter counts the numbers of. The rollover counter tells you how often the sequence number has been rolled over. That's all.
So if the sequence number does roll over,
yeah,
you start generating the same key stream again with the new sequence number?
No, that's what you want to avoid.
How is that avoided? What else is included in the calculation?
So normally the sender and receiver keep track of the rollover counter. They count it up, synchronized. But if you lose so that's possible as long as you have got a steady stream and you can tell the sequence number is increased one by one. But if you have got a network interruption and you reconnect again, you cannot tell how many rollovers happened in the meanwhile. And in this case, you need the protocol, either you establish a complete new connection and start the stream from the scratch, or SRGP provides a rollover counter as an attribute. And it would be very dangerous to establish a stream cipher again with using the same sequence number and maybe the same initialization vector again. So
So how is that prevented? What else is included after the sequence number rolls over? What else is included in the calculation of
the rollover counter gets into the counter. The rollover count, so this is, well, a 16-bit, and the rollover counter, well, using the rollover counter, you can calculate how often, well, you can calculate the offset and add the sequence number, the current sequence number. And that goes into the counter you use for the counter mode. Okay.
If you want to prevent different unauthenticated users to share the key, how often is it in practice possible to do rekeying?
Depends on your application. So if you've got a very unstable network that would cause mess of rekeying and so on, if you've got stable groups, and that's feasible. If you've got an unstable or very dynamic group, that's something you should avoid, the rekeying. But what you could do is yes. So now I thought about master key and maybe deriving a new key. Where is it? Here. Master key using a rate and the packet index. So the rate of messages being sent and the rate of messages being received could be used to derive an encryption key and an authentication key from the master key. So in this case, you would not need a rekeying, but in fact, that's easy to break.
So you would have the same effect as rekeying if you derived a different session key every n packets, And have you any practical experience how often you can do that?
No, I wouldn't do it for every 10 packets. So you might tell maybe a rekeying every 5 minutes or maybe every hour. So the rekeying might take place in a frequent way. So it depends on your application. Either you detect that someone left the group and you initialize a rekeying, or it's time-based rekeying every hour or what or so. So that might be sufficient.
Hi. Are there any differences or additional security concerns for between the different multicast modes, like PIM, sparse, smoke, dense, those?
PIM?
Does the security concerns change between different multicast modes?
No.
No. Okay. Thanks.
No. Okay. Thank you.